Hello guys, welcome to my channel, and in this video we'll talk about electrostatic potential. This is the second video of the second chapter, electrostatic potential and capacitance. In our previous video we talked about the introduction paragraph, and we see certain terms like potential energy, electrostatic potential energy, and we see that there is a charge, it creates an electric field, and when we move a test charge, that we call it test charge, in this field it will exert a force on it. So we have to exert external force, and we have to do certain amount of work against this field, and that was stored as potential energy in this. Okay, that we studied. Okay, there was certain point that we see in the previous chapter, like previous paragraph, like the charge should be of small magnitude. Okay, because it should not disturb the discharge, it should not exert force on this. We should apply force equal to the force exerted by the electrostatic force, so that there is no net acceleration. Okay, and yeah, this was the point we discussed. So now we'll talk about electrostatic potential. I read NCERT line by line, I explain it to you. Okay, so consider any general static charge configuration. We define potential energy of a test charge q in terms of the work done on the charge q. Okay, so as I told you that what was potential energy, the work done in bringing the charge. Okay, from actually the thing was, it was potentially different, that was significant. Okay, where the second point is, we have to move the charge from 2 points. Okay, if I am bringing it from infinity, and we generally take infinity as 0. Okay, potential energy infinity as 0. So when I bring it from infinity to this point, any point, then I'll say the potential difference or the potential of this point is the work done in bringing the charge from that infinity to that point. Okay, that we discuss. Yeah, and this work is obviously proportional to small q. Okay, obviously the if the magnitude of the charge is more, you see, if the magnitude of charge is more, suppose there is a charge, and suppose that charge is, suppose 10 coulomb. Okay, or suppose the charge is 1 coulomb. Okay, this is even a very big charge. Okay, so what happens, and if there is a 2 coulomb charge, so which charge will be, in which charge we have to exert more force to bring it to this point? You will say this charge, because the source charge will exert more force on this. As you know from Coulomb's law, that force is the directly proportional to the magnitude of the two charges. Okay, so in the case of the charge having larger magnitude, the work done will be more. Okay, and now this work is obviously proportional to small q, since the force at any point is QE, where is the electric field at that point due to the given charge configuration. Okay, so the work is, as I told you, that it is proportional to the magnitude of charge. Okay, now it is therefore convenient to divide the work by the amount of charge small q, so that the resulting quantity is independent of q. So we want a quantity that doesn't depend on this magnitude of the charge. You see here, the work done depends on the charge. The more the magnitude of the charge, the more will be the work done. But we want a quantity which is not dependent on this magnitude of charge. So what we'll do, we just divide the work done by this magnitude of the charge. So what we get, a quantity that we call as potential, and that will be the characteristic of that point. Okay, that will be the work done per unit charge with the characteristic of that point. How much the charge affect that point. Okay, how much effect the charge, the source charge, create at that point, that will be the potential of that point. Okay, it is independent of the charge. Okay, whether we place a charge or not, there will be a potential there. Okay, and when we put a charge there, then it have a certain potential energy. Okay, so now, in other words, work done per unit test charge is characteristic of the electric field associated with the charge configuration. Okay, this lead to the idea of electrostatic potential V due to given charge configuration. So there is a term electrostatic potential, will denote it by V, and this is what the work done per unit charge. Okay, we'll just divide the magnitude of charge by the work done, and we'll get this electric potential, and this will the characteristic of that field. Okay, now work done by external force in bringing a unit positive charge from point R to P is equal to Vp minus Vr, that is the potential difference of the 2 points. Okay, you see that when there were 2 points Rp. Okay, as you seen in the previous video. So when I move the charge from this point to this point, when I'm doing a work, okay, so what is happening, it is gaining certain potential energy, okay. So this is the potential energy difference. So suppose potential energy of R is UR and potential energy of P is UP. So what is the difference of UP minus UR? This is exactly the work we did, okay, in moving a charge from R to P, and divided by the magnitude of the charge will give the potential difference between the 2 points. Dividing the this work done by the magnitude of charge will give me the potential difference, okay, potential difference, okay. So this is Vp minus Vr for a unit charge, Vp minus Vr, okay. I think I hope you are getting it, where Vp and Vr are the electricity potential of at P and R respectively, okay. We are just dividing the potential work done or the potential difference by charge, so we are getting the potential difference, okay. Now notice before that is, it is not the actual value of potential but the potential difference that is physically significant, okay. As we discussed in the previous video that the significances of potential difference, energy difference, because we are talking about 2 point. Whenever we move a charge, we will move it from 2 point. We are stating it in terms of 2 point, okay. So when we're talking about potential, so the important is the potential difference is more significant, okay. Even when we talk about a potential of a point, we are saying that the other point is at infinity, okay. Now it is as before, as choose the potential to be 0 at infinity, okay. So this is the main thing you have to understand, that when you are talking about potential of a point, actually we are saying that potential is difference of that point with respect to infinity, okay. Where infinity we have chosen the potential of infinity as 0, okay. You are getting my point. So we'll move to the next paragraph. So work done by external force and bringing a unit positive charge from infinity to a point is equal to electrostatic potential at that point, okay. So what is the work done in bringing a unit positive charge from infinity to a point? Is simply the potential of that point, okay. In case of a unit positive charge, remind it, okay. If there was there was certain magnitude of the charge, it was not a unit charge, then we'll just simply multiply this potential with the charge magnitude, okay. Then we got the work done. So in terms of words, in other words, the electrostatic potential at any point in region with electrostatic field is the work done in bringing a unit positive charge from infinity to that point, okay. From this definition we can define work potential, electrostatic potential. It is the work done in moving a unit positive charge from infinity to a point on that field, okay. So this work done will be the electrostatic potential of that point, okay. Now the qualifying remark made earlier regarding potential energy also apply to the definition of the potential, okay. There were two qualifying remarks we made, like the charge should be small, the test charge should be small, so that it doesn't disturb the other charge, it doesn't exert force on the source charge, okay. And the other thing was we have to move the charge, we have to apply force equal to the electrostatic force, so that acceleration is 0, okay. Same applies here. To obtain the work done per unit test charge, we should take an infinitesimal test charge del q, obtain the work done del w in bringing it from infinity to the point, and determine the ratio del w upon del q, okay. So again we take a very small charge del q, and we'll determine the work done from infinity to that point, okay, small work done, and that divide the ratio, and we'll get the potential of that point. Also the external force at every point of the path is equal to the equivalent opposite to the electrostatic force on the test at that point. This is already discussed, that at every point what force, external force we are applying should be equal to the force exerted by the electric field, okay. I hope I'm able to make you clear this paragraph. So in the next video we'll talk about potential due to a point charge, okay. Like this video if you find this helpful, okay, share with your friends, and you can give your feedback on where should I improve in my in the explanation, okay. So thanks for watching.